So good afternoon. We are going to start the next session, which is about inks and papyrus. So our first speaker is Cristina Gamberini from University of Modena, and she's going to talk about some analysis of ancient black pigments from Roman archaeological sites. Please.
Yes. Okay. Perfect. Hi, everybody. Thank you for being here. Also, even if the afternoon, after the lunchtime. So we will talk about. We spend just a few minutes talking about spectroscopy, structural and spectroscopy analysis of Asian black pigments from archaeological sites coming from Italy. What is our analytical procedure? Well, actually, our analytical procedure is a complex one. We start with optical microscope for to distinguish homogeneity, heterogeneity of the powder. We will talk about powder. And then we use ultraviolet light to determine the presence of binder, organic and mineral colorants, if present. And then in our lab, we have SEM, so SEM scanning. No? Yes, thank you.
Because there are no...
There's no... you can give me.
No, there was something here, sorry. It's there.
Huh? Is it okay? Okay. And we use a scan electron microscope for to understand morphology of the powder, and also X-ray diffraction to identify, quantify the powder. And we have spectroscopists, chemists, so vibrational spectroscopies, FTIR and Raman spectroscopy, as you know, for possible to define the presence of clay organic binders and to define, identify or other materials and organic compounds with such technique also. What we use why we use also micro-Raman spectroscopies, because it is a non-invasively and non-destructive technique, and also we can use the same sample and study with other non-invasively technique. And it's also possible to identify with this technique mineral and organic components inside complex matrix, and also contaminants of processing and environment contaminants too. So we will use for a screening technique for study a lot of sample. You will understand how many samples we usually manage. So this is just an example of some images of one sample, of one of the 1,000 samples, and here the abundance of element, just to have an idea. For those of them are not chemists, but all of them you know very well this. And this is just two examples of Raman and FTI spectra. Yes, we study powder, yes, in organics, quite simple. What we study in other samples, quite difficult. So we study the shoulder and the shoulder and the shoulder, and we assign each band and each band to a ligand, a vibrational spectroscopy. So usually we make also the segment of all the bands. Yes, we do also X-ray diffraction, so powder diffraction, but in this case we had a lot of, the pattern was not so good, so we had to come in a high resolution beamline to have all the patterns selected and with a good result. So what was our project to come here? Well, actually, Philippe Alter and Martinetto has told me, why don't you come and analysis and to do analysis of all your sample to have good result. And Catherine Dijon helped us a lot in the beamline ID 22. Without our help, we couldn't manage for a long time, 1 week, day and night, and all these measurements. You will see how many samples she did for us. Thank you, Catherine. And also, Pierre Olivier now he works a lot and is still working on the results, and is still working to have the result that you will see just part of them. So where the power came from? It came from ancient orders that archaeologists told us they were orders for Asian cosmetic holder, and they were Pisidae. They told us, because my friends are archaeologists, also no chemists. Also, so Pisidae, used for cosmetic, atramentum was used for inks, unguentarum balsamarum for cosmetic usage. So all the powders usually at first are analyzed with our vibrational spectroscopy. So FTIR, micro-Raman also says technique too. For the most difficult sample. Then I came here in beamline ID22 with the sample. Yes, but not all of them, because all of them are really lots. Yes, there were black powders, gray powder, pink powder, and white powder. I brought here just the black powder. Well, actually, there were 133 black powders and found inside the Asian orders. The Asian orders that we expected were 1,300. And from the first microanalysis, carbon black was present, and vegetable and bone black we found due to some bands in some spectra and in some order, not all of them. So I came here with more or less 50 samples coming from different places in Italy, so coming from Colano and Pompeii, and also from Sicily. So I went in marvelous place. I was very lucky. I went in Mozia Island, a marvelous island near Trapani, Baglianseo Museum, and also Salinas in Palermo. Here is the setup of ID22 with high resolution, high energy of resolution for X-ray diffraction. So the detector and the sample put inside the capillary. The experiment in ID22, so 50 samples, we have tried to put, I say try because inside the little capillary, usually we broke and also the capillary sometimes, and the power was not too much, so we had to be quick, but also to fill all the capillary, and the sample was put on a magnetic stand, and due to robotic arm, it's possible to study all these samples in ID22. And ID22, with the help of Catherine, we could do analysis all night and day, during the morning and during the night also. Thank you again. So here is just an example of our sample. High resolution X-ray diffraction. You will see at first the first pattern. At low energy, we could Pierre Olivier could study the amorphous part of carbon black. And here just the optical image of the sample put inside the capillary. Here is an example of a sample coming from a Colano of the patterns, how it could so good just only here, because in our instrument with the resolution in Unimore, we couldn't have these results. So all these results were and are still elaborate with Retrival refinement to have a good answer. So here is just to understand that the crystal part of the black powder fit exactly, and the residue from the crystal part was the amorphous part of carbon black. At point 1, point 2, we observed the distant carbon to carbon, and at point 2.4, we observe the distance, the two carbon to the neighbor to the other one. So a good results are coming, but you've seen that the samples are really a lot of sample. So this is just a table of some of the results. So in the first column, you will see the sample with the inventory number, and the inventory number is the inventory number of the oldest. You can see some picture of the old inside on the other part near to the column. And then in the second column is the crystalline phase, the quantification of the crystalline phase. Well, and then the XRF results of the little percentages of the oxide present. And yes, we could, you can focus your attention on the green. We could have a good result, and I found the black carbon in some samples. Yes, usually these black carbon were vegetable. We are not so lucky here to find the bone black. So what is our challenge? Our challenge, yes, is to study thousands and thousands of samples. Yes, we have more or less 2,000 samples all in my lab. So you can't find any more in the oldest, if you want to go there. And yes, but we want to have a connection, more knowledge between the ancient oldest and what found inside. So to have a connection and what the ancient oldest made of. In conclusion, we can say that the ancient powder found inside the ancient olders, so Atramentum, Guentarium, Balsamarium, and Piside, can be studied with a multi-analytical approach techniques, not just one. Well, actually, we are talking about just powder, and so we are talking about laser. You know that if a matrix organic was present, I couldn't use this, but perhaps Raman SARS, but I had to use GC-mass and other technique also. So Raman spectroscopy can be useful for screening thousands of samples to have identification, not quantification, only with the XIR, X-ray powder diffraction, and only here in Grenoble AD 22, it was possible identification and composition of this powder. Yes, are no destructive samples, so we can use for other analysis if we need, and also we have major knowledge between the holders and their containers. I have to knowledge again all the persons that are still working in the project. Other names are not written here because there were other two persons helping us. So I have to thank again Martinetto and Philippe Baltet. They asked me to come here, and Catherine, that she worked a lot, and Pierre Olivier for the XR pattern diffraction. So thank you a lot for your attention, and do you want to come with me in this marvelous place? Why not? Okay.
Thank you very much. Do we have any questions?
Thank you for a nice talk. Just a question. Measuring inks on the herculaneum papyri, on the top, on the written herculaneum papyri, not in inkwell as you do, ink coming from herculaneum, okay? But herculaneum papyri.
Yeah.
Papyrus?
Papyri, yes, I haven't done papyri, okay.
I do that.
Okay.
So
Me no.
Yeah, but what we found at TSRF, but also in the library itself with the portable XRF, practically systematically, Olivier can confirm, we found metal in inks. So it's not pure carbon-based Atramentum, etc.
Okay.
So.
Well, actually, with Raman, is yes, and also other technique, it is possible to find metal. Well, so
a large amount. We found
no, we didn't. Well, actually, for example, in PCD there was present carbonite, but lead carbonate. It rotates, so it becomes a basic lead carbonate, if you think about this. But other kind, yes, well, hematite was lead acid of I don't know the name in English, farro. And then the West, but metal, no, we didn't find.
If you go back to your table, there is something which is really interesting.
Yep.
As a continuation of
I have to come back.
what Victor showed this or explained this morning, is that it's the one which is 11432. So the one which is in the second third of your table, a phase very minor. You say phosphoediphan, and this is extremely interesting because it is a bit similar to what Victor mentioned this morning. This lead calcium phosphate. And this result for us is very interesting because when we found lead and phosphorus and as lead phosphates, not on the, or possibly on the herculaneum papyrus, but on Egyptian papyrus, immediately the first question is it something which forms in situ? Because of the phosphorus which will come from the environment. The fact that you find it in the ink independently of the papyrus is a very good clue that phosphates are already in the ink and they are not coming from the environment. So I think there is really something to explore more on this kind of phases here.
Where from this sample?
The sample is coming from
Pompeii.
Pompeii. Yeah.
Related to that point Vito made, just from curiosity, would you see in Raman spectroscopy galena, the lead sulfide?
Well, sulfur of mercury. Lead, yeah, no, not AKGS. I don't know the name. Mercury,
No,
yes.
PBS.
And also PB, carbonate PB, but carbonated. Carbonated, basic carbonated, so PB.
The question was if you have detected lead sulfide.
No,
galena.
lead sulfide, no.
No. Okay.
Okay, so if there are no more questions, thanks again. And our next speakers are Professor Lepper and Manke from Berlin. And they are going to talk about papyri.
Okay, thank you. No.
Sorry. This one?
Yes.
And this is pointer.
Okay. All right, thank you very much for having me today. I'm going to share some exciting results about retrieval of the lost literature from the herculaneum papyri with X-ray fluorescence microscopy. My name is Luxi Li. I'm a beamline scientist in Advanced Photon Source Argonne National Lab. In this presentation, I'm going to give a brief history of the herculaneum papyri and the fundamentals of the technique that we are going to use, the X-ray fluorescence microscopy. And then later on, I'm going to talk about some results from the phantom, the test samples, to test the logistics of our hypothesis. And then we scan some real samples, the papyri fragments, to see, to read the letters inside the papyri fragments. So, is my voice continuous or is broken? Okay. So here's a simulation. Here's a simulation of the Mount Vesuvius eruption. So at that time, this pyroclastic flow buried a few Roman settlements in the neighborhood, in this vicinity, such as Pompeii and Herculaneum. And there is a private library that collected a huge amount of papyrus rolls near Herculaneum, was buried during the eruption. And this collection of papyrus stayed undisturbed until the middle of the 18th century when it was first discovered. And ever since, hundreds of papyrus rolls were unearthed from the site. And the conventional way to study these papyrus rolls is to physically open them and to read the content inside. However, this is a successful example of unrolling papyrus. However, for most of the case, it's impossible to avoid damaging them from physically unrolling. This is because the temperature of the pyroclastic flow can reach up to 300 degrees. So once the flow flooded this area, that immediately carbonized these papyrus rolls, made them extremely fragile. And since they're stored over almost 2,000 years, because of the pressure and the environmental fluctuation, these layers of papyrus can get stuck together, and with the pressures and the weight, they crumble, they deform completely. So it's impossible to unroll them. This is an example of a well-preserved herculaneum papyrus. You can see it's a big chunk of black carbon type of roll, so it's impossible to open them. And so that's a lucky case, but most of the times we find them broken or damaged, and there are small fragments scattered around the site like these. So these are the samples we scanned for this research. So with the physically unrolling impossible, so scientists start to reach for the non-destructive method, and X-ray because X-ray has a strong penetration power, so that gives us the possibility to study these papyrus rolls in situ without unrolling them. And with advent of the third generation synchrotron, that gives us really high X-ray flux, that makes us easily to study with X-ray CT to resolve the 3D structure of the papyrus. But unfortunately, the absorption contrast between the carbon-based ink and the papyrus are so weak, so it's impossible to read the content inside. And then later on, my collaborator, Dr. Mochella, in the audience, so he and his collaborators used the X-ray phase contrast tomography, and they succeeded to read, to view partially the letters and some words in situ without unrolling these papyrus rolls. But this method is computational intensive. So later on, we thought about how about X-ray fluorescence, because this technique is very sensitive to trace element, so it can detect up to sub-ppm concentration. So what if we study the elemental distribution in the 3D fashion that is that contained in the ink component? So this is what we think that might be possible. One way to retrieve the letters inside the papyrus. Here's the fundamental of X-ray fluorescence. So when the incident X-ray, if the energy is equal to or higher than the binding energy of the inner shell electron, it tends to ionize the inner shell electron, leaving a vacancy. So at this state, the atoms are very unstable. Therefore, the outer shell electrons turn to fall in this vacancy. In the meantime, it meets an X-ray photon. And the energy of this X-ray photon equals to the energy difference between these two electronic states. And this energy is characteristic to element species. Hence, if we can measure the energy of these characteristic X-ray emission as well as the intensity, we're able to identify the element species and quantify them in the X-ray illumination volume. Here's a schematic of X-ray fluorescence microscope. Here's a picture of APS. A specific energy X-rays is selected by monochromator from synchrotron radiation. Then it's focused onto the sample. So the spot size of the X-ray defines the limit of the X-ray fluorescence images. Now we have a fluorescence detector located perpendicular to the sample. Usually it's an energy dispersive detector that detects a full spectrum from the sample illumination volume. Here's the detection logistics. So if the X-ray is fixed onto one point in the big sample, or if the X-ray is larger than the sample, so it's considered to be point detection. And this is the detector readout. It gives a full spectrum. So basically, by analyzing these peak positions in terms of energy and their integrated intensity, we're able to tell the element species and the concentration in this detection volume. And then if we raster scan the sample and then do the same analysis for every single pixels and then deconvolute them into element maps, here's an example of what we see, for example, chlorine, potassium, rubidium, and then overlap them for later data explanation. Then in terms of 3D mapping, there are two geometries. One is in the projection geometry. We call it X-ray fluorescence tomography. In terms of data collection, it's very similar. So we take 2D projective XRF images and then rotate the sample so that we get projections at multiple projection angles. And then we analyze the data and deconvolute into element maps. Later on, we sort these projections by element species and then run 3D reconstruction with normal tomography algorithm. Since X-ray fluorescence microscopy is a scanning probe, the data collection is very time consuming. And also there's self-absorption issues with this technique. However, with, for example, the ESRF upgrade and later the APSU, the X-ray intensity will be increased dramatically, so that will reduce the total data acquisition time dramatically. So that's one of the advantage of the upgrade of the current synchrotron radiation facilities. And there's another geometry. So this is a top view of the instrument. So all of the setup is very similar, except for we put a focusing optics in front of the detector. So that allows us only detect fluorescence signal from a specific depth in the sample. So this way, we just go to different, so by adjusting the detector to sample distance, we're able to detect slices in the sample in depth. However, because it only detects a few percentage of the total extra fluorescence signal, so the signal level is really low. It requires much higher X-ray beam. Again, this technique will definitely benefit from the upgrade in the synchrotron radiation source. All right, so once we go through the schematic of the technique, first thing we do is to scan some synthetic sample to test the feasibility of this work. So we are proposing, by studying the 3D distribution of lead, we're able to identify the letters underneath the top layer. So this is a modern papyrus. So we laid 3 layers. Each of them has letters that are written in lead-rich ink. So we stack them together and then scan it with confocal XRF mode. So this is a 3D reconstruction of the lead signal. You can see we can clearly identify the letters throughout the 3 layers. And they're not exactly flat, but we can clearly recover the letters from the top layer all the way to the last. Once we got the proof of concept, then we scan some real sample. So this is a small papyrus fragment, about 1 centimeter in diameter, but the thickness is very, very thin, about 200 microns. So that may consist of a couple of layers of papyrus. And we can see, even from the visible light microscope, you can see there's an O-shaped letter on the surface. So that's our first attempt. Hopefully, we can see the zinc distribution that agree with the letter. So here's an integrated spectrum of a 2D scan from this sample. So we add up all the signals over all the pixels. That gives us good signal-to-noise ratio. So we can see here the common elements that from papyrus. It may vary from the source. And then here are the possible elements that come from ink. We have lead, mercury, iron, copper, sulfur, phosphate. And from the integrated spectrum, we can see most of the elements. And if we focus on lead L line and lead M line, we can see there's a significant amount of lead inside the sample. So, however, if we go to 2D distribution, these are the element maps of these commonly seen elements. And we overlap calcium, which is rich in papyrus itself, and then iron and lead. We pretty much see lead overlap with the other 2 elements, which means lead distribute evenly inside the sample. So that leaves us with the question, where does the lead come from? So this may come from the water during the manufacture of the papyri. And then we tried a different sample with a much thicker size. It is about 2 millimeter in thickness. So there are 2 letters that are quite visible from the surface. And then we did slightly different approach. So we scanned it in the projection fluorescence geometry. And over this area that is supposed to have letters, lead signal doesn't show up anything. However, there's this spot that lights up. It seems it has a huge amount of lead in this area. So we zoom in, to see this area. And then we see a Y-shaped letter. And also the size is about 2 millimeter by 4 millimeter, which roughly agrees to the size of the characters. And then, so we run a fluorescence tomography scan, and this is the lead reconstruction that we got from the data. And then you can see this character is quite deformed. So this is this might come from the long time storage under its current condition. All right. I want to thank my collaborators, and all this experiment were done in APS. Thank you very much. I'm glad to take questions, and then if later on, if you want to discuss with me, feel free to email me. Thank you very much.
Thank you. So we have time for one or maybe two questions.
Maybe one comment about lead. I think we are going to find it more and more in ink. I mean, it seems that your collection, we found it. In herculaneum, we found it in, there is another poster from a collection from Copenhagen where we've also found it. And I think this is really not a contamination, but it's really an ingredient which is part of the formulation. And what we are working on now, as you found lead as lead soaps, and we also found them as lead soaps. So more and more, I mean, at least but maybe more people have the idea that lead was used really for the formulation of ink, possibly for maybe a dryer, possibly of the binder. So my guess is that more than a contamination, it is really something which was used on purpose to modify the properties of ink. But, well, we will see.
Yeah.
On this point of view, what I know is that on this point of view, one fragment of the herculaneum papyri was identified with the lead as ink. I think is one in the Louvre collection. I did some analysis on other herculaneum papyri which are in the Museum of Naples, and I found lead everywhere in the papyrus.
Yeah,
so
like what I show over there,
yeah,
it's evenly distributed
like
throughout the sample.
And we were thinking about some contamination by the environment,
so you mean
after this is an hypothesis anyway.
You detected lead in
everywhere.
the papyrus, independently of ink.
Yeah, everywhere,
okay.
everywhere.
Yeah.
But it can also be. I mean, we can also envisage that then it was a papyrus which was prepared in some way.
It's possible.
Yeah, these are
to prepare the surface for writing with something which contains lead.
Maybe Olivier knows better because he also made a lot of measurement in library in Naples. Finally, we found, correct me, in all, at least all the Greek papyri, because there are 10% that are Latin. There were metal in all the Greek, sometimes iron, sometimes, but up to us, Marine should remember, the amount we found of lead is pretty high, cannot be contamination because it's very, very high. What we found in one single fragment is extremely high. So, but sure there is lead in water. So
yeah, you can see the lead signal is quite strong, and it's for this case it's evenly distributed.
So there is lead in papyrus somehow, but the amount we found in measurement in years ago
exactly, but
it's too high. It's too high. Too. I didn't remember now, but extremely high. In one fragment, the correlation of the amount of lead was incompatible with the contamination, honestly. But
it shouldn't be surprising if lead white was used to brighten the writing surface, and in later times, Islamic manuscripts are often burnished with lead white, just in the way that vellum might be burnished with chalk to make a whiter, more dense surface, and also to control the way the ink flows on the surface. I once had to transport a copy of the Quran back to Turkey through airport security, and it was absolutely opaque in the X-ray machine. Because of that, it was a big problem.
And this reminds me that, always on this question about lead phosphates, where is it coming from? And we have the only text so far that we have where we have a mixture of lead white and bone white, which could be the starting step, is so far from Cennini, which is explaining how to coat parchments for drawings or writing. So it may be something, an explanation for the presence of lead as well, like preparing the surface for a later use of the papyrus. Yeah.
It looks to me we have all the possibilities from
All possible explanations.
lead everywhere, from almost no contrast, a bit of lead, but
Yeah.
almost no contrast. So, yeah, probably it need to
Probably,
depends on the
yeah.
time.
Well, there is contrast sometimes.
Sometimes.
Yeah, like this one. It's quite obvious, right? You see this letter stand out in lead map in comparison to other ones, other elements. I want to make a comment to the previous talks that I remember the audience asked about. Is it possible that this ink contains lead phosphate?
Phosphates, yeah.
Phosphate. So I mean, in this case, because I don't see anything in the sulfur except for it looks like it's a surface structure. But again, with extrafluorescence tomography, we have the self-absorption issue. So like the fluorescence energy with sulfur is 2.3 keV. So if the sample is thick enough, the signal may not be able to penetrate through the sample and just get absorbed on the way propagating to the detector. So this way, it's really hard to tell if there's a sulfur counterpart respectively to lead inside the sample.
Yeah, it's important. Indeed.
So, right, because over here we see pretty much the signal from the more towards the surface.
Yeah, indeed. We detected it a couple of times because we were under vacuum at ID21, so we had the possibility we had a very good sensitivity to phosphorus, and also because the samples that we measured, the ink was on the surface, but in your case it may be a bit challenging indeed to probe the signal, and let's say to give link phosphorus to an ink which would be internal to the...
Right, it might be difficult to tell if it's lead carbonate or phosphate or sulfate. But this way, at least we can use the zinc, the lead signal to read the letter.
Then we should go to diffraction.
Because the energy is high, so it has a much stronger penetration power.
Okay. So I think we need to move on. Thanks again for all the speakers of this session.
Okay, so I'm going to be the chair for the next two talks. My name's Andy Goetz. We're moving on to an area which is maybe hasn't been addressed up to now, but is about using machine learning and deep learning artificial intelligence techniques. I think there's going to be a lot of there's a lot of potential here for the work that you're doing, because some of it's very time-consuming.
And can I just move through?
We had a workshop here 2 months ago, which was very successful. You can still find all the talks online, so if you want to have a look about applying machine learning and artificial intelligence to photon and neutron science. So the first speaker is James Brusuelas from Kentucky, and he'll tell us some more.
Thank you. Thank you for inviting me. So yes, I'm James Brusuelas from the University of Kentucky, and I represent a larger research team led by Brent Seals. And like most of the teams evident here, we truly are an interdisciplinary team in what we're trying to do. And we're very interested, like most people here, in extracting non-invasively content from, well, it's just hidden and trapped inside damaged culture artifacts, in particular one that has come up many times in this conference. The Herculaneum papyri scrolls. With a lovely introduction to the background, the eruption of Vesuvius, I fortunately don't have to go into all that. We can kind of stay on time here. And just looking at the variety of intact scrolls and also open fragments. But really, it's getting into that this intact scroll is the big problem and the large challenge. For our virtual unwrapping, I'm sure most people are familiar with the fact that, yes, we have a nice process for virtual unwrapping, and this was successfully applied to the carbonized parchment scroll from Eingetti, in which Dr. Seals' team, before I actually was hired and brought to Kentucky, did successfully virtually unroll it, and that text was deciphered very quickly as a text of Leviticus. And in this sense, I think we're all familiar with the fact that the iron gall ink is largely the culprit for why we could read this so clearly. It just readily appeared in the tomography. So what I'm going to talk about today really is the kind of the logic behind the deep learning approach that we've been experimenting with. And this comes down essentially to our concept, or just the concept of the morphology of what we're dealing with here. And this image here, just papyrus, inked papyrus under an electron microscope, what we're trying to isolate is the structure here. We can see the papyrus and we can see the ink. There it is again. Now what I'm about to show you here is just more close-ups, is a oversimplification of the process, but it'll kind of convey what's going on here. So in this instance, if we have our raised surface, which is our fiber, basically whether it's iron gall or carbon, it gets applied, it sits on top, but also soaks in. And this is essentially the signal that we're going for in applying deep learning. Now, in the case of Eingetti, when you get it under the tomography, it's bright and it's legible, and so it's mostly, it's going to look like this. Problem with carbon is that usually every time we try this approach, this is essentially what we're getting, right? It's, the fibers are there, but nothing is there. But what we're really focusing on is the fact that it isn't invisible. It is there. It's just coming up with the recipe, the cocktail, so to speak, to find that signal, isolate it, and amplify it using deep learning and artificial intelligence, whatever we wish to call it. So our emerging principles here are the morphology. The ink as a layer on the substrate changes the shape of the surface. That's the signal. But we need to capture the micro-CT at a high enough resolution to show this ink evidence, to tease it out, something to lock onto. And this is our process of deep learning. Going to the carbon phantom, we're just going to kind of walk you through the general process of starting up the test scenario, the training scenario, based on our phantom. Here we've got 6 columns, and this represents essentially thickness of ink, starting with 1, just 1 pass of carbon ink. 2 increases the amount of ink over and over and over again. You can see that the thickness increases by just looking at the Greek letter shapes. That delta or the theta or the sigma just gets thicker over across. And we also have our numbers, and we got our bullet points, which are in iron gall. As an example here, we get our expected result, right, if you put it in tomography. And column 2, can't really see it. We can see the 2, we can see the points because those are iron gall. Middle, we just have the phantom. And 3 represents the creation of labels, creating the masks, creating the training labels, because now what you're going to do is you're going to create these because of where you know where you're at, because of that iron gall. You know that that ink has to sit in there. So this is how you create those training labels. And it's an iterative process over and over and over again, with the critical fact being, at the end of the day, to really assess your deep learning algorithm, your AI approach, is how good is it at predicting across something it does not know or it has not seen. So it's essential to have that leave one out. The overall process here that we're looking to insert this method into is just basically this. We got our volume, we acquire the CT, we apply the virtual unwrapping pipeline, we align to reference, we create these labels. What we're looking for here, essentially at this stage, if you want to think about what the machine knows, what the machine does not know, how is it learning, what is it thinking about? Right now, it's really just thinking in the confines of ink versus no ink. Here's our phantom again. Here's the entire phantom under the CT. Now, what's interesting here is, yes, you can still see all those dots, you can still see the iron gall, but if you really look closely at the image, the thicker the strokes, the more times we took that pen and wrote over the delta, wrote over the sigma, and increased it, made it thick, the ghost actually almost seems like it starts to appear. What you're looking at here is a result of the convolutional neural network based on how it's trained, based on all those labels, going over those sections, and then also going to the point of leave one out, pass it over something it does not know. Here we can see that that just standard one stroke, just write delta once with the ink. It does have problems. It can't really tease it out. It can't find it. It's not differentiating ink, no ink. Go down the rows. Yes, the thicker it is, it can latch onto a signal, and that signal can be amplified to tease that stuff out. We even did simple tests in the sense of, well, let's just not focus on ink at all. Let's just look at the RGB. Have the convolutional network think in terms of, can it predict and classify black versus tan with the carbon phantom? What you get at the end of the day with the output solely based on this carbon phantom and the training labels that were created is you can generate this. And what's critical about this image is that it is a generated image from the output of the neural network. So what we understand here is that yes, using this approach, you can train you can apply deep learning to basically take that CT scan data, latch onto this, that signal, amplify the letter shapes, and create a photorealistic representation. What's also interesting here is it's not even so much just the letter shapes. If you look closely, it is identifying and picking up on the pattern of the fibers themselves and doing a decent job at recreating that as well. Just a kind of an overview of what you've got here with this essential training based on our phantom. Top row, we got the phantom, we have the CT, we've got the output of the neural network, and then this photorealistic regeneration of it. What it's coming down to in the minds of our computer scientists, I am actually digital humanities papyrologist classicist. I'm not a formal computer scientist, even though I tend to absorb, and I am absorbing more and more just working with this team, is that it's often explained as a resolution, almost a numbers game. At what resolution do we need to be to isolate that morphology, to isolate that signal? Right now, based on our research, we're kind of thinking that you probably need to be somewhere in the range of probably at least around 10 microns, somewhere between 10 to 2, maybe 3 microns, to where we can hope that we can actually have this deep learning approach that can latch onto that signal and start to amplify it. We did recently, back in September of last year, go to Diamond Light, the synchrotron there at Oxford, to do some scanning with the p-Herc scrolls from the Institut de France. Here's a nice image of Brent and Madame Berard. Now, what also should be noted here is that in doing this research in general, for us, it's not just working at the level of how to apply the computer science methods, the deep learning methods, digital humanities methods, papyrology. There's a level of conservation that goes in, it's involved here, because to get these scrolls, and in this instance, the I-12 beam, we do actually have to create custom cases so that we can mount them in the beam. And these are simply, well, not simply, these are created using photogrammetry to capture the topography of the idiosyncrasy of each scroll, and then basically 3D print them out so that they can be placed inside very carefully and mounted in that beam. Now, the diamond data is just coming to us. We're only now at the stage of beginning to process and play with the reconstructions, but we do have some images, fortunately, to show you here today. So here's basically p-Herc Paris 3 at 25 microns, 8 microns. There's some close-up shots. Again, conveying that right now for The approach that we're taking is we need to get in there at the resolution that we think we require for the deep learning method to work. Let's see if it's stuck. Come on. Oh, and finally, here's just some vertical slices I wanted to show you as well. And we got some nice animation video to kind of show you the internal structure. And it's going to look kind of like what we're already used to from prior imaging. It looks just like it's a mess in terms of thinking about how to go about segmenting that in the end. But that's part of the fun. So this engine for discovery, this idea of getting in there to really truly extract mass amounts of text, to actually read text, identify text locked inside these intact scrolls. It's going to be a process of acquisition, segmentation, texturing, but with the texturing, putting a layer of deep learning on it to actually extract that text. And then, of course, flattening, merging, and then ultimately reading, scholarship on these texts. What I'm going to end with here to kind of convey further the process, the reason why we're pushing and following this path, is right here. This is Object 59, which also belongs to the Institut de France, which was just put in a conventional SkyScan CT scanner at UCLA last year as well. Now, because it is an open fragment, because there actually is ink on the top, this is an opportunity to basically test the deep learning process from another angle, because we truly believe the way to really unlock all of that text inside is going to require the open fragments to provide you the training data that you ultimately need. So what we have here is just, again, looking close up, what we kind of expect for the herculaneum fragments under CT scan conditions. But here what we're going to do in this experiment, and some of you may have seen this because Dr. Seals has presented this somewhat recently, back in October at the Getty. We split this in half, where we used the left side as the training side, and we used the opposite side to classify, run it over something it hasn't been trained on. So what we're looking at here in the video that we're about to show is we're looking for the amplification of a Greek letter roughly the size of this delta. And as somebody that does read Greek and as a papyrologist, I can categorically tell you that yes, I do see the amplification of the omega, which is there. So where we're at now with, and I'll wrap it up, keep us on time. What we're at with the diamond data is it's not just immediately throwing the deep learning process as it currently exists at that data, mainly because that data is immense. The sheer size of it not only requires, well, it requires us to basically refine and keep working on the existing tools because of, you know, it's in, I forget how many terabytes that data is, but it's large. And so right now it's an exciting moment because we're now getting it and we're going to start to basically throw what we currently have at it to see if, or to see what the process is going to be down the road for applying our method to start fully extracting large amounts of texts from something either under a layer, hopefully, if we actually apply some of these methods to open fragments, but really getting at those intact scrolls. Thank you.
Questions? Any questions?
Too impressive, Anna.
I have a color question. In some of your letter, I saw the letter identified in white, sometimes in black. I guess that the color map is the same.
Yeah, well, so basically this is an instance of you code within the algorithm itself what color you want it to actually pop up. So why you're seeing it is basically you're seeing it white because we basically are having it amplified in that.
No, I understand, but is more absorption white or is less absorption?
Don't
is
know
white
if I'm following
is more
you.
absorbing, so let's say lead, metal that absorb more?
Well, in this instance, we're not really, yeah, it's not, the process right now isn't based on absorption. Right now, the process is based on training the machine to understand at the level of resolution that we have what is papyrus and what has changed the topography on top of it.
I understand the algorithm, but your rough data are essentially radiography, tomography, etc. So if you use the same color map, white should be more absorbing or less absorbing. After you can have any algorithm you want to enhance signal, but it's more absorbing than background or less absorbing than background?
I don't know if at the end of the day, what the question I think you're asking doesn't apply to the technique that's been applied. It's not that it potentially cannot and not have influences on adding to it, but right now the machine isn't thinking in terms of absorption.
No, I understand that the machine does know, but physics behind should know.
I don't have a response at that at this time then.
Thank you.
I had a question, which is, what is the most time-consuming part of this process? Is it the segmentation or the?
It's probably a little bit both. I think at the end of the day, for the intact scrolls, the segmentation will appear just as challenging as the amount of time that has gone into the deep learning method.
And have you thought of applying deep learning to segmentation?
Yeah, so we're also we do have students that are working on the process of automating segmentation, because at the end of the day, when you look at that volume structure, that internal structure, to do it manually by hand just doesn't seem very appealing. And for sheer accuracy, the amount of times it's going to have to go over to get that segment out, we would prefer to have that automated.
Yeah.
But again, because of the sheer size of the data based on the resolution, it requires another level of iterating on the code, on the algorithms that you've already created to get it to work properly down the road.
Are we talking of years? Yeah.
No, well, I couldn't put a finger. I won't come out and guarantee you when it's going to happen. But what I can say is I think we feel confident that we're on the track to, in a very timely fashion, hopefully, start to extract large amounts of text from basically like a bit of segmentation. But when you can do it an entire scroll, that I do not know, and that will take much more time, I think, down the road. Because it depends on the internal structure. Not all intact scrolls are basically going to be the same in terms of how they were damaged. So you might find one that, for whatever reason, doesn't have all the bumps and bruises, all the contusions and contortions. And so it becomes a better case for virtual unrolling because of that circular circumference structure is still kind of there. So segmentation process can go faster. But as soon as you look at something that looks like a rat's nest or like a bunch of strands of jewelry like thrown together and you got to peel it apart, that's painful.
So it means eventually we'll come through, we'll read the whole scroll.
That's the idea. That's the idea.
Yeah, okay. Thank you. Yeah, I was interested to see, in addition to the actual relief that you're going to get by the ink, you will also get a contrast between a kind of textureless surface left by the ink and a fibrous surface of bare papyrus, right? Is it going to be able to pick that up?
Yeah, so that's also on the list with the new diamond data, is improving our methods for looking at what's in the neighborhood, right? Mm-hmm. Because the more features that you can teach the machine to recognize and then it can classify, the better prediction rate you're gonna get at what is that morphological feature that is the ink. So no, that's correct. That's on the to-do list now.
Excellent, thank
you. So correct me if I'm wrong, but if I understood well, basically whatever difference would be below your label of the letter can be recognized by the deep learning as an information. So what I mean is, even if you have no clue if it is a texture, if it is a relief, if it is absorption, phase contrast, whatever, as soon as there is any difference that you would probably never spot by eyes, the system can train on that.
Correct. That's what AI, regardless of application, cultural heritage, or specifically we're seeing this in medicine. That's where it's exceeding predictions by radiologists in determining cancer, because it's just going to find things that we are not seeing.
So typically the thing is, if you can have more information, whatever it is, you will have better results. So did you already try to make, for instance, multiple energy scans? So you make several times the same scan, you change a bit the spectrum, because you will just have more information to give to your system.
Yes. Yeah, we did that a couple of years ago. So,
I think we did.
yeah, my colleague here's got more information. I think she can answer that.
We did different scans. Oh, I'm sorry. We did different energy scans when we scanned the samples at Diamond in September.
Okay.
So we're just beginning to process all of that data. But yeah.
Yeah. No, again, you're spot on too. Right now, we're at the point where the more information, the better for the deep learning approach.
Hello. Thank you for the talk. I have a naive question because I'm not expert at all in neural networks. I would like to ask you, the learning set was on the left side of the fragment. I suppose it was Greek letters. But now imagine that actually it was a dictionary, and on the right you had Latin letters. Is there a bias?
No, because again, it's not thinking about alphabets. It right now at this level, it does not care. The only thing it's thinking about is, I understand what the substrate papyrus, what the fibers are, and what I'm looking for is a pattern in the data, which are these bumps. And so right now, it just starts to highlight that. So whatever the shape that results, it could be Latin, it could be Greek, it could be anything.
Could be a drawing.
Yeah, it could be drawings as well.
Okay, very, very interesting. Thank you very much, James. Well, thank you. And the mic.
Oh.
Thank you.
Before I walk away with the mic.
Okay. So now we have Johann Briffa. Yes. And then you're going to continue as well. So I'm very keen to hear this because we've been exchanging a few emails because I was a bit involved in this project, and we hear some more about it here. It sounds very promising. But I won't steal their thunder.
Perfect. Control L, I think. Yeah, there you go. Okay. Thank you. I'm excited to talk to you about the ASEMI project, which is basically a collaboration between a group of us at the University of Malta in the Department of Communications and Computer Engineering, and Paul and a few other guys here at the SRF. So ASEMI is about the automated segmentation of microtomography imaging. So basically the project itself is funded by Attract, which is an H2020 project. So that's the funding context that we're working on. It's been going on for the last few months. And I'll start with a brief overview of what the project is about, and then I'll hand over to Mark for details on the machine learning part of things. So once again, we're talking about mummies. Now I'm sure most of you are familiar with what mummies are. So these are basically ancient dead animals that have been mummified, so dried up and wrapped around with textiles and some other things done to them, and then left for a very long time. And one particular animal that we've been looking at quite a lot over the last few months is an ibis. So this is a modern one, but the one that we've actually been looking at is more like this. So this is a scan that Paul and Camille and so on here at the SRF have actually done. The one on the left is the actual image. The one on the right is simply brightened up because I know that on projectors you don't really get to see the contrast well enough. So this hopefully gives you a slightly better idea. Now, what's the fundamental problem that we're looking at? What we're trying to do is to automate the labeling process, which is right now basically done manually. So we start with what's on the left, which is the scan, and what we want to end up with is the image on the right, where every separate pixel for every slice, so every voxel effectively, needs to be labeled with, what is it? Is it bone, marked in red over here? Is it the ceramic jar that simply closes everything in this case? Is it soft tissue? Is it textiles that wrap the mummy? Now, why do we care about this? The whole point of identifying all these is so that, and this is where I would really like to show you something that Camille and Paul produced, and she'll be talking more about this later on. So this is a 3D view that they did. Sorry, there's a video that they did of the 3D scan itself. So right now it's just going through the various layers. And after they did the labeling manually, which took quite a long time, then they could start looking at every component separately. So this is the whole point. So once we're through with that, then you can see it in force color. But more interestingly, you can actually start carving things up. So you can remove virtually the ceramic. You can start looking at the textiles. You notice that some of them are pretty degraded on the outside. So we can remove those as well. And what remains is the wrappings, the tighter wrappings around the mummy, with some bones protruding in this case. And again, these can be removed because everything that is segmented separately can be seen separately. This is the key point behind all this. So once you remove those, you can see the soft tissue. You remove that, you start seeing the bones. And this gives you insight into what's within the mummy so that the archaeologists can start to do their actual work. So all this, in a sense, is just preparatory. And this is basically where we come in, because doing this manually takes a very, very, very long time. We're talking at least weeks for something small, months for something like the crocodile that Camille mentioned yesterday. So the whole point of applying machines is that we now want to be able to do all that automatically. Now, why is that? It's not just that we want to make it faster to do a segmentation and therefore study of a single mummy, but there are many, many mummies. Camille mentioned already, for example, that in a particular site, millions of dog mummies have been found. Now, if you want to study one mummy, it's one thing. If you want to study many mummies and start having statistical data on them, then you need to segment many mummies. And there is no way that that can be done manually right now. So automation is key. It's critically important here. So this is the context of where we come in. So at this point, I'd like to hand over to Mark, who will talk to you about the various machine learning approaches that we've tried over the last few months and what we intend to work on beyond that.
Right. So I'm the guy who's doing the actual project on machine learning here. And first of all, it's important to point out that we don't use deep learning, even though that's what is implied in the program. But we do use machine learning because deep learning is something that we intend to do later. So basically, the idea is this. We have these slices, right? And in this particular volume, there are 4,500 slices. And rather than having to label each one of those 4,500 slices, we would instead like to have a sample of slices that a human would label manually, and then the computer would infer from that information how to generalize over the unlabeled slices. So basically, instead of having to label 4,500 slices, you just label 6, and then the rest is done automatically, right? And that would be great. So for example, here we see the terracotta, and the human would say, this is what the terracotta is. And that can be drawn either by a pen or something. Then you move on to a slice that's further along, and the computer has to guess where the terracotta is. And this is what the computer says, right? So this is not, a human didn't do this, the computer did, based on the information that it learned from the previous slice. if we see then, for example, something more interesting like bone, right? This is also what the computer thinks is bone, based on what the previous slice it found. So for example, this is here, right? It found that this is a bone. This, it's saying that it's a bone, even though it's an inclusion, but we might forgive it for that. I would imagine that it's a bone as well. Textile, sorry, if we compare it to what a human would say, right? This is the manually labeled version of bone. We can see that it's actually very similar. We see textile, so the wrapping around the mummy. It's confusing a bit of tissue with textile. So the stuff inside here is the mummy itself. And it seems that there's a lot of similarity between textile and tissue. And so that tends to get confused a bit. But tissue seems to be very hard to label even for people. So that can be something that we should work on later. And tissue, right? So again, some differences that we can see. For example, this is inside a bone. Here it's being considered as tissue, the marrow inside the bone. Here it's considered as part of the bone, right? Now, if we want to quantify that in terms of numbers, how well it's doing, we can take what the manually labeled part of a bone is, for example, and what the computer is labeling as a bone, and divide the area of the intersection by the area of the union, right? And that gives you a measure of overlap as a percentage. If it's 100%, that means that's a perfect fit. And we see that air and terracotta are being labeled very well. Tissues are the hardest to label, but in general, it's in fact, Paul was quite happy with it when we sent a segmented volume. So we still have some work to do, but we're quite happy as well. In terms of time, this takes about 46 seconds per slice, which means that if you want to do all the 4,500 slices, it takes about 2.5 days. Of course, we have found some bottlenecks. We can make this faster. And that is also something we intend to work on right after this conference, basically. Right, so how does this work? As I said, it's not a deep learning method, but it is a machine learning method. So the idea in segmentation is that you want to take each and every one of these pixels and classify them. You want to choose, you want the computer to tell whether it's bone, whether it's tissue, whether it's textile, etc. But it has to be done for each and every pixel. Now, in this particular specimen, we have about 3 million pixels, right? And so it has to do this one by one for every pixel. And in order to do that, it needs to extract some kind of information about that particular pixel in order to allow the computer to, based on the information about the pixel, tell what label it is. And the information would be the neighborhood, we call it, around that pixel. We used a random forest classifier to do that, which is quite a common machine learning method. We also tried other things like SVMs and logistic regression, but the random forest works best, we found. But you also need to provide manually engineered features, which is the information that describes the voxel. And we tried several things like SIFT features, which are used in photos, local binary patterns, which are used to describe texture in photos as well, and histograms, And that's what we found works the fastest and also gives good performance. And the idea is this. Extract a cube around that pixel, right? So extract a cube of voxel intensities around that pixel. And construct this list of numbers. The voxel value, so the amount of the intensity of that voxel that you're classifying, that's very important to include. A histogram of a small neighborhood around the, so a small cube around that voxel. By histogram, I mean the frequencies of different intensities, of ranges of intensities, right, in a cube. And another histogram of a larger neighborhood. So it's like two levels of detail, right? There's a bird's eye view, and there's a more fine-grained view. When you do that, and you feed in, so you turn every one of these pixels into such a list of numbers, together with the manually selected label for the pixel, and you feed that to the random forest, the random forest will be trained in order to predict what the label should be based on those numbers. And you get and this is basically what we did for the results that I showed you before. So we used the voxel value, a cube that's 3 by 3 by 3 for the small neighborhood, and a cube for the large neighborhood, which is 41 by 41 by 41 voxels. And you get an 85.2% average intersection over union at a speed of 46 seconds per slice. Something else that we tried doing is to, rather than enlarge the neighborhood, instead we would make the volume smaller and then use a small neighborhood in that rescaled volume, because that is kind of equivalent, right? In image processing, this is called an image pyramid, and it would help because rather than having to collect a histogram for a large cube, which takes time, you can instead use a small cube in a smaller volume. And if you do that, you save some 2 seconds, so it's not a lot, but 2 seconds for a lot of slices, that adds up. But you get a reduction in the precision. These are the best 10 combinations that we have found. We've been trying all sorts of different combinations of how these, what works best. What's important is, what's interesting is, for example, using a very large neighborhood does not give you better performance than using a smaller one, right? So this means that you can't just pick one neighborhood size and apply it to everything. So this would probably mean that you will still need to train it on a specific specimens rather than train on one specimen and then apply to everything else. For future work, we intend to make the process faster. We intend to create a plugin so that it can be integrated into Dragonfly, so that you just press a button. And as I said, we'll be using deep learning in the near future. Thank you.
Okay, thank you. Any questions? Yeah.
So I noticed that the hollow bird or ibis bones, the interior was also classified as the outside. Is
Yes.
that because these features are a bit too small relative to your larger environment, or is there a reason why that was the case, or was this just in the example you showed?
So you're asking why it filled in the bones?
Yes.
Well, the thing is that, so if you zoom into there, this isn't really hollow. There is a bit of webbing in there, which is from the marrow. And the computer has approximated that, right? Because it can't learn a perfect model of what a bone looks like, but it makes these sort of subtle mistakes, and I don't know. We still have to compare these results with Paul in order to see what are actual labeling mistakes and what are sort of ambiguous mistakes, because even though these were labeled manually, there's still a bit of subjectivity, right? No two annotators will say the same thing.
If I may add something small, it also depends a lot on how the initial manual segmentation was done. So sometimes the manual segmentation would simply label the whole thing as a bone. Sometimes, so this depends on the person actually doing it. Sometimes they would prefer to clean up any internal cavities and remove them from the labeling. In that case, the training that the computer sees is different, and the output will also be different.
Yeah, I would like to add something regarding the segmentation of the skeleton. Basically, the computer made better job than us. So the thing is, most of the errors are coming from the fact that the manual segmentation we made is far from perfect. And for instance, you can see that you have some textile within the body that we were not segmenting during our manual segmentation, but in fact, the computer found some textiles there, and the error in our side, it's not the error of the computer. So the computer made also errors, so it's not perfect. But some of the things come really from errors in the manual segmentation, because you can never spend enough time. So you can consider that we are giving a good approximation of what it should be, but we are humans, we are making mistakes, and from time to time we also want to go to sleep. So it's I would say, yeah, the results were
But that's because you had to segment the whole volume. If you just had to segment 6 slices, you would make less errors.
Yeah, but we are not segmenting the full volume by hand, slice by slice. We made region growing, we made morphological operations and things like that. So, but again, we do that to have the best possible result in the shortest time. So that's why the masks are never perfect. So in this respect, many things that are considered as error from the computer can be also attributed to error of the humans from the beginning.
If I may, Paul, also there's certain inconsistencies on what's inside a bone. So is there air? Is there tissue? Right? They look kind of the same. Is it bone? Right? So it's
exactly what I mean. We made some
what's
mistakes
inside
even
a
for
bone
the
is not
skeleton.
consistently labeled either.
So the data we gave you, you have some bones that have been filled and other ones not. So it's really not the fault of the computer, I would say, in this case.
If you'll allow me a little practical question, how memory and operation heavy is this? I'm not a computer specialist, and I wish I was if I see this exciting work, but can I do this on a home computer or a
That's a very important question, and it's something that we've been struggling with since the beginning of this project. Yes, Johann?
Short answer, I think. Right now, the machines that we're using are fairly conventional workstations, so nothing fancy at all. We recently bought some larger memory machines, like 256 gigs RAM, that kind of stuff, to hopefully make things a bit faster. But to actually make it a lot faster, the best way forward, I think, would be offload much of the work onto the GPU But in terms of memory, memory is basically the biggest problem here. A single volume is something like 30 gigabytes. So if you want to load all that into memory, that's basically 30 gigs of RAM. And that's just having the copy there, not even doing anything with it. So yeah, mostly memory intensive, I think.
And if we're going to be working on larger volumes, right? Because eventually we're going to also be working on human mummies, for example. It's very important that it's fast and also memory friendly.
But I think 30 gigs is today not an issue. You could get a machine with a terabyte without a big budget. Yeah? So you could be. I mean, we
define big budget.
Well, we could provide you one, I'm sure. Okay, thank you, and thank the speakers again, both of them, and yes.